extreme values in the data, extreme small or extremely large or extremely small values in the data set, or if we have outliers in the data, okay, that can affect the standard deviation, okay. So this is useful really when we deal with symmetric data. Bell-shaped symmetric data is what we're going to talk about, okay? But what if we don't have symmetric data? Well, then there's other statistics that we can use in those cases that we'll cover in the next section, okay? So just to be aware, a note to write down of what we're talking about, okay, when it comes to using standard deviation, okay? Okay, let's see here. And the reason why is because those extreme values can make the standard deviation, either sigma or S, the population standard deviation or the sample standard deviation, very large or very small, okay? Let's see here. Okay, so a couple other things too. Is now that we've spent time on standard deviation, I want to now talk about another measurement of dispersion which is directly related to standard deviation. Okay, and so once you see this, it'll be very easy because, like I said, that's why I want to spend time with standard deviation, because when I show you the calculation for variance, it's really easy. Okay, so now, here is okay, there's the sample standard deviation formula. Okay, sample standard deviation. Okay. The other statistic that we can calculate is variance. Variance is also the measurement of variation or dispersion in a data set. Okay, and it is directly related to the standard deviation. In fact, as you're going to find out, in order to calculate standard deviation, you have to calculate variance. In fact, that's what we've actually been doing, is calculating variance, and we haven't even, you haven't known about it until now. Well, here's how you calculate it. Okay, so here's standard deviation. To get variance, so in this case sample variance, it's just S squared. So literally all you're doing is taking the sample standard deviation and squaring it. So in other words, you're dropping the square root sign here. Because when you take the square root of this, or excuse me, when you take the square of this, you're undoing the radical, the square root. So literally the sample's variance is just this. And likewise, the population variance is done similarly. So that would be sigma squared, which is just the summation of x minus mu squared divided by capital N. So to go from standard deviation to variance, you're just dropping the square root. Or if you're going from variance to standard deviation, you're adding the square root. So either way you want to look at it. But that's variance. We don't use variance very much because it's harder to interpret. Mainly because of the units, because these have square units. So here you're talking about square units. Okay, so if your data is in inches, you're going to be talking about square inches as a way of measuring dispersion or how far away a particular value is from the mean. So you're looking at squared distances, which is hard to really comprehend and interpret. So standard deviation is very useful because you're dealing with the same units. So if the data is in inches, so is the standard deviation. So much easier to interpret, right? Because you're dealing with the same units. Okay? I hope that makes sense. Let's see here. Okay, so now the two main ones for measuring dispersion. Now there's one other calculation I'm not going to spend a lot of time on, but it's good as a starting point. It's a rough calculation, but it's quick and easy. Okay, so and that calculation is what we call the range. It is a measurement of spread. It's not a really good one. Okay, you've seen this before. I'm not going to spend a lot of time on it, but the range is a measurement of how spread out the data is. The problem is it's quick. You know, the good thing is it's quick. You only need 2 points, the max and the min, and you can calculate it very quickly. It's not very accurate because it's very sensitive to outliers, very sensitive to extreme values, right? So if you have a really large value that turns out to be an outlier, that's going to make a huge difference in the range, okay? So that's the only thing. It's quick, it's easy, not very accurate, not used very often, okay? So again, that's another measurement of spread, okay? I'm adding it because for completeness, okay? Let's see here. The other thing too that I want to mention when it comes to this topic is something called the coefficient of variation. Okay, so now that we've introduced variance and standard deviation, what if we want to compare two values? Standard deviation is very useful in comparing two values, comparing how if one population or one sample is more spread out or has more variation than another sample. Okay. And it's easy if you're dealing with samples that have the same mean or distributions that have the same mean. Then it's obvious. The one with the larger standard deviation has the data more spread out. Okay? I could also compare. I can use standard deviation to compare how far a particular value is from the mean, the center. Right? So if one value is one standard deviation from the mean, versus another observation that is 2 standard deviations from the mean, then I know that the one observation that's 2 standard deviations from the mean is further. Okay, it's farther from the mean. Okay. Now, what if I have 2 different populations with 2 different means and 2 different standard deviations? How do I compare them and decide which one is more spread out? Okay. If the means are significantly different, then it's not going to be as easy. It's going to be like an apples and oranges comparison. So one thing that we can do to make it more of an apples to apples comparison is to use the coefficient of variation. And the way you calculate that, and it's denoted CV, is to take the standard deviation and divide it by the mean. So in other words, if I'm looking at the population, I would just take the standard deviation sigma and divide it by the mean, mu. Okay? And that'll give me the correlation or the coefficient of variation. But then I also want to multiply it by 100% to make it into a percentage. So basically what I'm looking at is I'm comparing the standard deviation with respect to its mean for that distribution. So if I have 2 different populations, then I could calculate the coefficient of variation for each one because I would have a standard deviation and a mean for one population, and then I could calculate the same thing for the second population. And then what I'm doing is I'm basically looking at percentages. And the one with the highest percentage or the higher percentage has the higher variation relative to the mean. And I hope that makes sense. So again, very simple calculation, used to do comparisons, but again, not often used. But again, make sure you know how to calculate that if asked to, okay? I think that's about it. So that's it about the measurements of variation. So now what we're going to do is let's look at two general rules. Okay, so up until this point, all I've given you are ways of calculating statistics, measures of center and measures of variation, dispersion. Okay, so now that we've introduced standard deviation and the mean, now I want to introduce to you some things that you can deduce given whether you're given some information or not. Okay, so these general rules hinge on two, how should I say this? Are used based on whether you have certain information or not. Okay, so the first general rule, it's really a theorem, it's called Chebyshev's theorem. And you can apply this theorem on any situation as long as you know what the standard deviation is and the mean. Okay, so if you know the standard deviation and the mean of a population, and that's all you don't know anything else about the distribution, you don't know that it's skewed, symmetric, or what have you, then you can draw some conclusions using this theorem. Okay, so here's what the theorem states. Okay, so Chebyshev's theorem says this. If I don't know anything about the population, I know nothing about the distribution of the population, but all I'm given is the mean and standard deviation, the question is what can I say about the percentage of values that fall within certain values, certain standard deviations, okay? Then this is the best I can do, okay? So Chebyshev's theorem says that I'm going to use this formula to find the minimum percentage of data that falls between standard deviations, either one standard deviation, two standard deviations, within three standard deviations. That's what I'm referring to, okay? So let me write this out. So the minimum percentage of data falling within K standard deviations from the mean is equal to this formula, okay? And it's very simple. It's just 1 minus 1 over k squared, where k again is the number of standard deviations you want to be between, okay? So we're always talking about the middle percentage, okay? So for example, if I have a distribution that looks really weird, okay? But I know the mean and I know the standard deviation. So if I know the mean is here, let's say it's over here. Okay, let's say the mean is here. So mu is here. And let's say I'm going to go out 3 standard deviations this way. And I'll go out 3 standard deviations this way. Then what can I say about the percentage of data that falls between 2 standard deviations, or within 2 standard deviations of the mean. Well, this is what Chebyshev's theorem says. So if I take 2, for example, I can't do 1. So again, this is basically, again, I didn't say this, so this is under the restriction that k is at least 2. Okay, why? Well, because if you stick 1 in here, what do you get? Well, 1 divided by 1 is 1, and 1 minus 1 is 0, so 0% doesn't mean anything. Okay, so again, so we're going to start with 2. So if I want to know what percent of the data, the minimum percentage of data that could fall between those two values, then I would just plug in 2 for k. So this is going to be 1 minus 1 over 2 squared, which is going to equal 1 over, or excuse me, 1 minus 1 over 4, which is going to equal 3/4, which equals 75%. So we can know that there's at least a minimum, so there's a minimum of 75% of the data that falls between these two values, whatever those values turn out to be, because those values represent 2 standard deviations away from the mean, okay? That's the idea. And again, you could do this for 3 standard deviations. Okay, so for 3 standard deviations, if we did this for 3 standard deviations, and so k was equal to 3, we would get 3 squared, which would be 1 minus 1 over 9, which would equal 8/9, which is going to be approximately 88.9%, or 89% if you want to round to the nearest whole percentage. But again, that's going to be between these two values, you know, within 3 standard deviations. And that's how you apply Chebyshev's theorem. It only is applied to situations that you know the mean, standard deviation, but you don't know anything else about the population or the sample. You don't know anything about the distribution, okay? Does that make sense? Good. Okay, so now, what's the next general rule? Well, the next general rule is based on some new information, or extra information, more information, I should say. What if you do know something about the population distribution? What if you know that the population is bell-shaped and symmetric? What then? Does that change things? And the answer is yes, it does. If you know, at the very least, you know that the population is bell-shaped and symmetric, then you can apply another rule and be more accurate. So let's consider that. So what happens if you have bell-shaped and symmetric distribution? So let's say we have something like this. Okay, bell-shaped and symmetric. So okay, bell-shaped, symmetric. Okay. Well, if it's bell-shaped and symmetric, where's the mean? The mean's located right in the middle, right? So here's the mean. So again, in this case here, we know the mean, right? Mu. We know the population mean. We know the population standard deviation sigma. And this time we're saying, hey, we know the population is bell-shaped and symmetric in its distribution. Well, this is what happens. So let's do the same thing. Let's do 3 standard deviations to the right, 3 standard deviations to the left. Okay? And since this is bell-shaped and symmetric, our standard deviations will be the same on both sides as far as distance from the mean. So this will be sigma, 2 sigma, and 3 sigma. This will be negative sigma, negative 2 sigma, negative 3 sigma. Okay, so now, this rule is called the empirical rule. Okay? Some textbooks call it the 68, 95, 99.7 rule, but again, that's a mouthful. I just use the empirical rule. Most textbooks use the empirical rule. Okay? So this is what we're going to apply. So what happens in this case? Well, this is what you can approximate. Okay? This is what we know. So again, you can take this to the bank. You just memorize this. Okay? If it's bell-shaped and symmetric, then we know that approximately 68% of all of the data values will fall within one standard deviation of the mean. If we go up to 2 standard deviations on either side. So again, this is the middle percentage. Okay? If we're within 2 standard deviation, the percentage of data values jump up to 95%. Now remember, if we didn't know anything about the distribution, the best we could do at this point with the Chebyshev's theorem was 75%. Look at that. We jumped up to 95% accuracy as far as approximations. Okay? And this is not a minimum value. This is an approximate value. Okay? So that's another difference between Chebyshev's theorem. Chebyshev's theorem was a minimum percentage. Okay? This is an approximate percentage. Okay? Now, if we go up to 3 standard deviations, that number jumps up to 99.7% of the data. That means 99% of all values in the distribution, the population, or in your sample will fall between these 2 values, whatever they turn out to be. Okay? I'm not putting numbers in here because we're going to do an example, but again, this is in general. Okay? So this is what we call the empirical rule. Now, the other thing too about this is fantastic is not only do you know this, but if you memorize this, you can figure out all the pieces between each one of these values just by adding and subtracting percentages and using the fact that it's bell-shaped and symmetric. For example, if I know that 68% falls within these 2 numbers, within 1 standard deviation, and I know this is bell-shaped and symmetric, then what do I know about this half? It should be the same as this half. So in other words, I should be able to divide 68 in 2, and both halves should be the same. So that means 34% should be in both of these. Okay? Now, if I know that this is 95% within 2 standard deviations, then I know this half should be half of 95%, which is 47.5. So I know from here to here, so how do I want to do this? I know from here to here, right, is going to be half of 95% because of symmetry, then half of 95, so this piece here, this blue piece, will be 47.5%. Well, if I want this piece here, what would I do? I would subtract. I would subtract the 34% from this, and what do I end up getting? I end up getting 13.5%. And then, of course, if this is 13.5%, then what do you think this is going to be? The same, 13.5%. So 13.5% go here. Now, if we do the same thing with 99.7, right? Well, if we split this into half, what we'll find is half of it will be on this side, okay? And then half of it will be on this side. Or, what can we do? Here's a better way of doing it. Let's figure out what is in this piece right here. If we know that in the middle right here, all the way between these 2 numbers is 99.7%, what's left over for the tails? what does all of these percentages add up to? What should all of the data be adding up to? 100%. So now, if I look at the whole thing from within 3 standard deviations is 99.7% of the data, what falls outside of that in the tails, in this piece and this piece here? Well, that's 0.3. So if 0.3 is left over, well, that means half goes here and half goes here. So what ends up being in this tail? 0.15 and 0.15. Well, what does that leave left over? Well, you can add up all these percentages, subtract from 100, divide by 2, and you'll find that this is going to be 2.35, and this will be 2.35%, and that's the entire table. Now, you might be sitting there thinking, oh my gosh, that's a lot. Well, the thing is the more you write this out, you don't have to do this. You can actually get all the values. If you just start with this and just use the fact that I can divide, I can use symmetry, I can add and subtract these, I can answer, you can answer any question that's thrown at you based on the empirical rule and using whole number standard deviations, as long as you know this. Okay? So if you know this, you can get all of this easily. Okay? So, it makes sense? Good. Okay, so again, if you have any questions about this, email me, take notes. Again, I went through it a little bit differently than I usually do in class, but again, just to give you another way of viewing it. Okay. Let's see here. Okay, so last thing I want to talk about is outliers. Well, not the last thing, but close to it. Okay, so now, here we go. We want to talk about outliers. So outliers, as I mentioned before, is a value that is significantly far from the rest of the data. Okay? So, let's write that down. So an outlier, nope, I don't like this. Okay. Is any value that is significantly far from the rest of the data. Okay, so now that's the definition. So now, a couple things I want to talk about here. So when it comes to outliers, you want to make sure you look at the data carefully. Just because you have an outlier, let's say you end up having an outlier, doesn't automatically mean you should disregard that value and not include it in your analysis. You have to look at it carefully. If a value is a result, if an outlier is a result of some measurement error or some transposition where it was not fudged, but maybe it translated over incorrectly, or it was typed in incorrectly, right? Some human error, right? Then in those cases, yes, by all means, you want to delete it, notate that, delete it, do not include it in your analysis, okay? But if it turns out that it is an actual value, that it's not an error, then you don't want to delete that because that's going to give you important information about the population. Outliers can be used to gain great insight into what's going on in a population. Okay, so we never want to just willy-nilly just disregard outliers. Okay, so that's the main point I want to make here. Okay, so one common criteria that I'm going to introduce now. One common criteria that we use that is used in order to classify whether an observation is an outlier or not is to use the standard deviation. Okay, so again, since we've talked about standard deviation now, let's put that into practice as far as outliers go. So remember, standard deviation is a measurement of how far a value is from the mean. So what is the mean? The mean you could look at as the typical value, right? That you would expect in a population, right? That's the mean. So this is a typical value, an average value, right? So the further away a value is, we could look at that as the less likely it is, or the, what's the word I want to use? The less usual, right? So if we think of values around the mean as the usual values, right? The usual suspects, right? What you would expect a typical value to be, right? But the further away you get from the mean, the less usual it is, or the more unusual it becomes. So when does a value get too far away from the mean that it becomes an unusual value that we want to consider as an outlier? Well, here's a rule of thumb that you can use, okay, that is used. So here's one common rule. If a specific value falls outside 2 standard deviations of the mean. Okay, so think of that diagram, right? So what we're saying is if we have something like this, and we have the mean, let's say, right? And so we have 1 standard deviation, 2 standard deviations, 3 standard deviations. Again, this way we'll do the same thing. Okay? So what we're saying is, hey, if we have a particular value of x, if it falls either in this region, right? So if it's either greater than 2 standard deviations this way, or if it's greater than 2 standard deviations this way, so if it's small. So if it's too small or if it's too big, we're going to consider that value to be very unusual. So not likely to occur. If any values that are within this range, then we're going to say, hey, those are typical values. Okay? And that's what we're going to consider an outlier. So that's one common rule. We're going to talk about another rule when we get to box plots. So this is not the only rule that is used. It depends on the context. So we use another rule when we talk about box plots. But when we talk about distributions like bell-shaped and symmetric distributions, or later on when we talk about normal, this is the rule of thumb that we use, one of them. When we get to probability, we'll actually talk about another rule that's related to this, but from another side of the coin, I guess you could say. Okay? So again, this is the one you want to use for now until we get to other topics, but this is the way we can define or classify a particular value as an outlier, if it falls outside 2 standard deviations. Whatever those values are, again, whatever those values are, once we put a number to these, then we'll actually know, hey, if it falls above this number or if it falls below this number, we can consider them unusual or maybe even an outlier. Okay? Okay. Sometimes we even go out 3 standard deviations for outliers. Okay? Maybe 2 standard deviations would be unusual, 3 standard deviations could be an outlier. Okay? But again, that's the common rule that we use. Okay. And I think that's it. I don't have anything else I want to cover. Again, if you have any questions, reach out to me and let me know, or just go back to the PowerPoint presentations or anything like that. But again, I hope you enjoyed this. Next time, we're going to get into the last topic for this chapter, which is going to be on relative position. How do we compare 2 different values within a population, or 2 different values, one in each of 2 different populations? So we'll talk about that next time, and we'll get into box plots, which is going to be the last graphical display that we'll talk about. Have a great night. Bye-bye. Okay, good morning, good afternoon, or good evening, depending on when you're watching this video. But today I just want to take a few minutes. This is going to be a short video, and it's because I wanted to go over something that I had left off of a previous video regarding Chapter 1 material, and this is continuing on with the types of data or variables that we deal with. We were talking about categorical and numerical, or quantitative versus qualitative. So the one thing I want to talk about today is going to be levels of measurement. So levels of measurement refer to what we can do with data, and it has to do with certain characteristics of the data that we're collecting, or the variables that we're interested in. So each variable, depending on the data, is going to have a level of measurement, okay? So categorical is going to have certain levels of measurement. Numerical is going to have certain levels of measurement. So that's going to be the title of this video. And it's going to be a short video because there's 4 levels of measurement that we're going to discuss. And the first level of measurement is going to be only with categorical data. Okay, only deals with categorical data. And that level of measurement is nominal. So something that has a nominal level of measurement means that it can't be ranked. It doesn't have any kind of rank to it. It can't be, there's no order. Okay, so it doesn't matter the arrangement of the different values of it. And this is really only pertains to categorical data. So this would be an example of like eye color. Eye color is categorical, but there's no ranking or order to eye color, right? It doesn't matter what order you list them in, okay? There's no ranking, okay? So nominal data or nominal level of measurement means that there's no discernible order or rank. Another example of something that would be nominal would be like political party affiliation. Anything that's categorical and doesn't have a rank. Okay, so for example, if I say a categorical variable like year in school, right? Like freshman, sophomore, junior, senior. Now those are categorical variables, but that wouldn't be an example of nominal. They wouldn't have a nominal level of measurement because there's a ranking to them, right? As soon as they say freshman, you're first year, right? Second year, sophomore, so on and so forth. Okay, makes sense? Okay. Now, that type of data would have the second level of measurement that I'm going to refer to. So number 2, the second level, is what we call ordinal. Ordinal level of measurement. So this is categorical data that does have a rank. So again, year in school, freshman, sophomore, junior, senior would be an example of a ordinal level a level of measurement ordinal. Okay, so ordinal, there is a rank to the data. There is an order. Okay, it can be ranked. So think of ordinal, order. Okay, nominal, it's just name only, right? When we say nominal, it's by name, right? So it just doesn't matter, just by name. Ordinal, order, think of that. Okay, so again, things like year in school. You could even say first year, second year, third year, fourth year. even though you're using numerical values, those are actually still categorical because they don't really have any other meaning other than just a place value, okay? So a ranking, okay? So in some cases, you could have categorical data that's using numbers, but again, the numbers just represent a category. First year, freshman. Second year, sophomore. Things like that, okay? It'd be the same kind of thing if I say male or female. 0 is male, 1 is female. Even though I'm using numbers to represent either one of those, it's just a representative category. So in that case, male, female would be nominal data, even though I could represent them in a 1 or a 0 in that case, okay? So again, these would be used with categorical data. So this is categorical. Okay. Now the next two are pretty much used with numerical. So 3 and 4 would be used with numerical. And another example of ordinal data could be pain scale, right? So what's your level of pain from 0 to 10, okay? So that would be another type of ordinal data, okay? Numerical. So the next one, number 3, is what we're going to call an interval level of measurement. Okay. So an interval level of measurement is where we have numerical data and differences of the values make sense. So we can get meaning when we subtract numbers, okay? So that would be an example of a level of measurement, a data that has an interval level of measurement. So we can subtract values in the data and get meaning from those differences. Okay, so differences are meaningful. Okay, so an example of something that would have a variable that would have an interval level of measurement would be like year in school, right? Or years in the stock market. Okay, so we could have a year represent, right? So we could go from, let's say, 2003 to 2010, and so each year would be one of our data points, right? So we could say, okay, are we talking about year 2007, or are we talking about 2003, so on and so forth. And since the variable is year, we could take a difference between 2 years, and that would be meaningful, right? It would tell us how many years from point A to point B. So if we want to know, let's say we're talking about stock prices, and we say, okay, we want to know how the stock did from 2003 to 2007. Well, if we take the difference from 2007 to 2003, well, we're talking about a 4-year period. So over 4 years, how did things change? So that's meaningful, right? We know the difference. We know how long it took, right? So that difference tells us something. It tells us the number of years that have passed, right? So interval level of measurement means that we're talking about numerical values and differences are meaningful. Okay, but 0, and here's a key thing, 0 is meaningless. Okay, so it's numerical, the differences between numbers mean something, but the number 0, so 0 is just a placeholder. I don't think that should be hyphenated. I think it's just one word. In other words, zero doesn't represent the absence of something. And I'll explain that in a second. So what do I mean by that? It means that 0 in the data doesn't really mean the absence of something. Meaning, for example, if I talk about year, let's go back to the example of year. If the value of year equal to 0 doesn't mean the absence of year. It's just in the data as a place value. Like, so if I talk about year 0, I'm pointing to a specific period of time as a placeholder, a reference point, right? So that's a perfect, it just, the 0 just is a reference point, right? It's to allow us to make comparisons. So when I talk about year 0, I'm talking about a time in history, right? 0. Likewise, if I talk about temperature, specifically if I'm talking about degrees Celsius or degrees Fahrenheit, the temperature of 0 doesn't really mean the absence of heat. It's a place value. It's a marking point of how cold or hot something is compared to another value. But 0 doesn't mean that there's no heat, right? So if I say 0 degrees Fahrenheit, that doesn't mean that at 0 degrees Fahrenheit there's absolutely no heat, okay? If I talk about 0 degrees Celsius, again, I'm not, 0 degrees Celsius doesn't tell me that there's absolutely no heat, right? It can be 0 degrees outside and it could be very cold, but it doesn't mean that there's no heat. Okay, it's just a place value in that case. So even in temperature, 0 doesn't really mean anything in that case. It doesn't mean that there's absolutely no heat. I hope that makes sense. Okay? So in those cases, those values, we can subtract values, and differences of values mean something, right? So I can subtract temperatures, and that will give me some meaningful information. I can subtract years, and that will give me some meaningful information. But in both those cases, because 0 doesn't really mean the absence of something, it's more of a reference point, then that would be interval levels of measurement. Okay? Now, let's go to the fourth one. And let me erase this for a moment. Okay. And the last one that I'm going to write down is ratio level of measurement. So that's the last one we're going to talk about, the fourth one. And the ratio level of measurement has many of the qualities of interval, okay? Except it has a couple of added. So ratio level of measurement, so a variable that would have a ratio level of measurement would also have differences that make sense. So it has the qualities of interval, except it has some extra qualities that interval doesn't have, okay? So a ratio level of measurement it's numerical, differences are meaningful, just like with interval, except that 0 in this case is meaningful. 0 does represent the absence of something. Okay? So let me write that down. So let me just write this down. So I'm going to repeat some of the things with interval. So differences are meaningful. Okay? And in this case, 0 is meaningful. So, in other words, 0 does represent the absence of something. Okay? So an example of something that would fall into this category of where 0 would be meaningful is weight. So if you put something on a scale and the scale says 0, what does that mean? It doesn't weigh anything, okay? So in the case of weight, when you have a 0 weight, it means it's weightless. It has no weight, right? So there's the absence of weight. Okay, so in that case, weight would fall not into this category. It has interval, right? So I can take differences, right? So I can subtract one person's weight from another person's weight, and that difference is meaningful. It tells me how much more one person weighs or how much less one person weighs compared to another person. Okay? So it has those two qualities. So it has differences are meaningful. It has 0 means something with weight. The other thing is that goes with ratio, and it goes right from the name. So think of interval, differences, subtraction, you get differences, interval. With ratio, not only do you have an interval, but you can also take the ratio of two values, and the ratio is meaningful. So that's the other thing. So ratios of numbers or observations are meaningful. Now think of the year example, right? So let's say we're taking year, right? We could subtract years, right? We could say 2003 to 2007, like we did before. We can subtract those two numbers, and we get 4. And we know, hey, 4 is meaningful. It means the number of years that it took to get from 2003 to 2007, right? But if we take the ratio of 2 years, right? If I take the ratio of 2003 and 2007, does that tell me anything? No, it's meaningless. It's completely meaningless, right? So that's one of the distinctions between interval and ratio. In ratio, levels of measurement, 0 is meaningful and ratios are meaningful. Okay, so it has to have those two things in order to be ratio level of measurement. Okay, so weight meets all of these criteria. So difference in weights, good. 0 in the measurement of weights means something, means the absence of weight. And then I can take the ratio of two weights. So I can take the ratio of one person, his weight or her weight, with another person's weight, and that ratio will tell me something. It'll tell me, hey, how much more in percentage-wise, let's say, is one person heavier or lighter than the other? Like I could take the ratio of two weights and say, oh, okay, well this person is 50% heavier or 30% lighter than another person, right? So ratios mean something, okay? So that's really all I wanted to go over for levels of measurement. So these are the 4 levels of measurement. You're going to want to know these, okay? If you're in a basic stat class, probably these wouldn't be important. And of course, you know, these are obviously based on what class you're taking. If you are in business statistics or a higher level introductory stat class, then these are something that you're probably going to want to know and be tested on. Okay, and so this goes again with chapter 1. So this was part of chapter 1 that I forgot to go over in that video. So this is an added video, and I'll probably just put it under the video on my channel under levels of measurement, chapter 1. So again, if you have any questions, reach out to me or talk to me later. Okay, thank you very much.